Hello everyone, and welcome to today's workshop on ice monitoring for the Copernicus WEkEO service. My name is Gaëlena Sterbik, and I'm a Training and Capacity Development Officer at Mercator Ocean International, and I'll be your host for today. So over the course of this training, we will explore key aspects of the WEkEO platform and its data. And on today's session, we will tell you what the WEkEO service is about, what sort of data and products you can find, and what sorts of application you can do with it. So before we start, let's quickly go over some house rules and guidelines to make sure you enjoy this webinar. First, we ask you not to use the chat that you will see on your right-hand side. So you can use it for small talk or to say hello to us, but if you have a more technical question or a content-related question, we invite you to use the dedicated Q&A section. So concerning the Q&A dedicated section, you will find the Q&A button at the top of your screen. So I'm sorry, the slides are moving a bit slow. Just keep talking while the slides move. But yeah, on the top bar of your screen, you will see the Q&A button. And if you don't see it, we will also put the link to the Q&A app on the chat. So no worries about that. So simply click on it to open the dedicated space, and you can ask our speakers your question of today. And while you're there, you will also find a quick survey about this training workshop, so feel free to fill it out anytime during the session. And concerning the agenda of today, we will have plenty of presentations. So we will start with an introduction. Okay. We will start with an introduction to the WEkEO service, so I will give you that. And then we will have a presentation of the Copernicus Pan-European Ice Products by Mathieu Denisel from Magelium, a service provider of EEA. And then we will have a QGIS plugin presentation by Michael Lund from the European Environment Agency. After that, we will have Annalena Erdmann from UMETSAT. She will present to us some WEkEO tools, so the Graphic Processing Unit and Earthkit, which is an open source Python development led by ECMWF for speeding up weather and climate science workflow. And then after a short break, we will have 3 presentations about specific application of this Copernicus product. So we will have Andrea Spaloar from the Institute of Polar Sciences in Italy. And then we will have Etienne Berthier from the French National Center for Scientific Research. And finally, Michel Tsamados from the University College London. So there will be the 3 use cases of today. And yeah, we hope you will enjoy their presentations. So yeah, now we will start with the small introduction of WEkEO and Copernicus. Okay, so I will give you this presentation. Okay, it seems I have an issue with the slides. I'm sorry for the little delay. Okay. I don't know why my slides are not moving. I think it should work. Okay, sorry for the delay. Okay, so for the introduction to WEkEO and Copernicus. So Copernicus is the Earth observation component of the European Union's space program dedicated to monitoring our planet and its environment. It provides free and openly accessible information services based on satellite observations and in situ data. So it helps service providers, public authorities, and organizations to improve quality of life in Europe and beyond. Copernicus operates through space-based and in-situ observation components and offers dedicated information services through self-standing portals tailored to various users' community. So if you want to access the data, Copernicus offers a lot of valuable environmental data across its various services. So WEkEO has been designed to bring all this information together in one convenient place. So instead of navigating multiple platforms, you can access original data from all Copernicus services and Sentinel missions directly through WEkEO. Whether your focus is on marine, land, atmosphere, or climate data, the platform provides a unified and efficient environment to explore and work with this data. So a quick overview of the WEkEO services. With WEkEO, it's quite easy to get started. You don't need any registration to view, explore, and discover the range of available data. Everything is open for you to browse freely on the website. So if you'd like to take advantage of more advanced features, you can create a free account to access personal working environments, cloud resources, and advanced tool and computing services. WEkEO also gives you access to over 400 datasets from Sentinel missions and the Copernicus atmosphere, climate, land, and ocean services. To help you explore this data, two tools are available: the Expert Data Viewer, which provides a detailed interface for data visualization, and the new Light Data Viewer, designed for faster and easier visualizations. So on the second day, we will explore the Expert Data Viewer during the second day of the webinar, as I said. WEkEO also offers a Jupyter Notebook gallery with over 100 ready-to-use notebooks developed across the Copernicus services. So you can view notebooks directly, clone them via GitLab to customize for your needs, or launch them in the WEkEO Jupyter Hub if you are a registered user. So this growing collection of notebooks cover a range of topics and workflows to help you learn and apply best practices when working with Copernicus data. The WEkEO Workspace, so the formerly known WEkEO Jupyter Hub, goes beyond just Jupyter Notebook, offering a full Jupyter Lab environment where you can explore data, perform basic analysis, and follow interactive workflow. So it's suitable for everyone, from beginners to advanced users. And it includes access to the Jupyter Lab, RStudio, and the Xcube viewer for visualizing data cubes. So for this workspace, it requires a registered WEkEO account. Then the WEkEO Drive, so it provides registered users with secure online storage to save, manage, and share their work directly within the platform. So these features support seamless collaboration and easy access to files used or generated in the WEkEO Workspace. You also have a set of advanced tools available, which are designed to help you scale up your data access and make your workflows more efficient and effective. So these tools are particularly useful if you're working with large data sets, running complex analysis, or looking for ways to simplify data handling and processing directly in the cloud. So these tools include the Harmonized Data Access API, and the WEkEO tools Earthkit and EOCanvas. So also for users with advanced data processing needs, WEkEO offers scalable cloud computing resources designed to support both research activities and operational workloads. So these resources fall into the two main categories to match different user profiles and project requirements. So I will not go into much more details, but feel free to look on the website for more details if you're interested. And finally, WEkEO offers dedicated expert support to help you make the most of the platform. So whether you're just getting started or tackling more advanced tasks, you'll find a comprehensive help center with over 50 detailed articles covering a wide range of topics. You can also get instant assistance by asking a question to our AI agent. So you can see on the yellow bubble here. And you can also chat directly with a member of the support team through the live chat widget. So yeah, easily accessible at the bottom right corner of every page on the website. And that's it for me for the introduction to Copernicus and WEkEO. If you have any questions, don't hesitate to ask them on the Q&A section or use the link available in the chat. And we will go to the next presentation, which is Mathieu Denisel from Magillium about the Copernicus iCover presentation. Welcome, Mathieu.
Hi. Hi, I hope you can hear me.
Yeah, we can hear you and see you.
Yes, thank you for the introduction. I will share my screen. Can you see the slides now?
Yeah, we can see the slides. Thanks.
All right. Thank you, Gael, and good morning, everyone. So I'm here to talk to you about the ice product that we generate in the frame of the HRWSI product, which is a Copernicus project. So I'm going to give you a brief overview of the project. First of all, HRWSI stands for High Resolution Water, Snow and Ice. So this is what we do. We produce some water, snow and ice cover maps across Europe. This is an operational service which is hosted on WEkEO. So we use some VMs and S3 buckets that are included in WEkEO. This project is supervised by the European Environment Agency in the frame of the CLMS, the Copernicus Land Monitoring Service. And it is made by some company like Geovil and NBO from Austria, FMI from Finland, and also CNES, Magillium, and support from the CNES from France. The main objective of the project is to monitor snow, ice, and water cover at high resolution over Europe. So high resolution is achieved thanks to Sentinel-1 and Sentinel-2 data, which have both high spatial and temporal resolution. The product we generate cover Europe, so it's EA38 plus UK domain. And we have been disseminating products in near real time from January 2025, and the whole archive is expected to be computed by mid-2026. And last information is that products are computed on Sentinel-2 tiles, even the Sentinel-1 products. The question we can wonder is why we should monitor ice dynamics. So there are a few thematic areas which we identified. The first one would be water management, that it is necessary to monitor ice conditions, like for dams, for instance. Also, transportation is important, like ice, frozen rivers can hinder shipping, and also we can say that frozen rivers and lakes could be part of some traffic road network. Then we can talk about biodiversity and ecosystem. Obviously, seasonal ice cover has direct and also indirect effects on flora and fauna. And finally, we can talk about climate change because the lake ice cover has been identified by the GCOS as an essential climate variable. So I've been giving you an overview of the project, and now I wanted to show you the products, starting with the Sentinel-2 water and ice cover products. So on the right side, you can see the RGB image, and next to it, you can see the WEkEO layer. So this product is computed in near real time, and it has a 20-meter spatial resolution. And the whole Sentinel-2 image is classified simultaneously with open water, ice, cloud, and other features, what we call them. It can be vegetation, land, or whatever. The algorithm of the WEkEO product is based on a random forest classifier, and within the product you can also find some quality layers, including a probability layer, also quality flags, and then a QA, which is a confidence score with 4 possible levels of confidence. There's the WEkEO and there is also the WEkEO, so the water and ice cover based on Sentinel-1 data, which is also distributed in near real time, and it has a 60-meter spatial resolution. Within this product, there is classification over inland waters, rivers and lake, basically. So we have the information whether the pixel is water, ice, or it can be unclassifiable because of radar shadow, layover, or foreshortening. The algorithm is based on a thresholding method, and in the product you can also find some quality layers, the QA flags and the QA, which are the same as the WEkEO as in the WEkEO product. Then I will show you this ice cover duration, which is an annual product, which is computed on a hydrological year from the 1st of September until the 31st of August of the next year. So it's not calendar year, it's hydrological year. This product has a 20-meter spatial resolution, and it gives you the number of days of ice cover over inland waters. As you can see on the image, so it's a number between 0 and 366. This product is generated by interpolating all the weak products of the year, and with the ICD layer, we also have some additional layer, such as the NOPS1, which is the number of observation for Sentinel-1. Same for NOPS2, number of observation for Sentinel-2, and also this QA layer, which is the confidence score. The last product I wanted to mention here is the A-week product. So it's different from the others because it's not a raster. So this one is daily, and it's an aggregation of the week product. So you have some statistics computed over lakes or 10 kilometer sections of rivers. So if you take a look at the table on the image, you can see that for each acquisition, you can have the number of pixels. Like, for example, if you take a look at the first line, it's on this observation, 82% of the lake was water, 2% was ice, etc. So this one is stored as a geodatabase, and it's disseminated a bit differently from the others. I will show you later. The conclusion here is that products are already available with a Python script, which is available on GitHub, on EA's GitHub. So all the products are available with the first Python script, and A-week is distributed with a different Python script. You should know that the portfolio will be integrated in the CDSE by the end of the year, and that our products will be validated by an independent consortium next year. Also, the new satellites which were launched this year, so S1C and S2C, will be integrated in the production. If you have any question, you can contact me, and also I added the help desk link from the CLMS. Thank you, everyone.
Thanks a lot, Mathieu, for your presentation. It was really interesting. We have a few questions for you, but we will do that after Michael's presentation.
Right.
So welcome, Michael, and hi. And whenever you want, you can start your presentation when you're ready.
Yes, I'll start sharing my screen. Okay. Can you see it now? Or?
Yeah, we can see your screen.
Yes. Hello. I want to present or demo the Copernicus Connect, which is a plugin created by EA for QGIS. and it's available on the QGIS repository, so it's easy to install. Just go to the plugins in the top, manage install plugins, and search for Copernicus Connect. And you can see I have already installed it, and as it says, it's an easy way to browse, download, and visualize Copernicus data into your QGIS setup. So when you have installed it, then you can run it, of course, but you need to have a WEkEO account for accessing the datasets, just as on the WEkEO page. And when you install it, it will ask for username and password, and there is also a link for that. So when you have installed it, you can open it, and it's docked on your QGIS, and you can undock it, etc. So it consists of this window on the right side here. We have two tabs, one for datasets and one for WMS and WMTS. So you can select between those. And in the top, we have some settings. Of course, the user, as I told you, should be a WEkEO user. There is also a link to the registration page. So when you have those information, then it should be ready to go. And then there is terms and conditions. So for each dataset, there are some terms and conditions depending on the providers, but you can approve them here or wait until you download it. But you can approve it in advance here. And you can also read the terms and conditions for each provider. And then you have, if you're downloading, you have a path where it's just a default path where you want to download your files. And when you do a search or request for data, then some might return thousands of files, so you can set a max limit here. Okay, so here we have all the datasets exposed from WEkEO, and right now there is 1,170 datasets, so it can be hard to find, but there is a filter up here at the top where you have the possibility to select, you can write snow plus cover, which means snow and cover, so both words should be in it. And or you could say snow pipe cover, which means snow or cover, or snow cover as a phrase. So if I write, for example, ice plus snow, then both words should be in here. And I can either click enter or at the update button on the left. And then we see we have 22 data sets containing both ice and snow in it. And if we take the first one, then we have those two tabs. So if we go to WMS or WMTS, we have the available services here. So if we click on the first one, we can see we have, for example, the service age of sea ice. And if I click on it, then I have the information in the selected layer down here, the information we use for opening it in QGIS. So we can either click add to layers or just double click on it. And then you can see it opens in the QGIS. And this is a time series, so the layer age of sea ice supports temporal data. So we say, okay, and you can see at the top, it will open this slice bar. So now we can use all the settings built in QGIS to look at the different dates, how it looks like here, using the slider, just as you can in WEkEO at the bottom of the web page. So this is a way, and you can open more layer if you want, just double click, and it will be added to, and you can see the layers on the left side in QGIS over here in the layers tab. But no. Okay, so when you have those, you can work with the web service. It's easy way to open service or to find service, just find your data set. And if we have some information about there is any WMS or WMTS added, then we'll show it here. But if we want to download data sets, the datasets, we can go to the dataset. But I'll just try now. If we take high resolution layers, for example, I guess it's not that much eyes on those, but just to show another example is here we have 6 number of datasets, and here we can go to the dataset tab and then show query parameters. This is dynamic generated depending, so the parameters depends on the dataset. Some have a lot of parameters to fill out, and some have few, like this one. And those marked with the red asterisk means that they are mandatory. So here, of course, the dataset that we have selected, and then we have a bounding box here, which means that if we want to just request data from, for example, the area Denmark, we can click Draw Bounding Box, select the area, and you can also modify afterwards the area with using the vertex tool up here. And you can see now we have selected this bounding box. We have automatically filled in the coordinates from the bounding box. But we can also select canvas, extend from the canvas layer, so which means the whole window, the coordinates from that one. So it will change again the coordinates in here in the bounding box. And we can select the other areas that we have, or yeah, just generate. So in this way you can select your area. And then you have the product type, which is a variable here. And for example, this one, and here the resolution is the only one you can select, and it should be selected, so that's why it's grayed out or disabled. You can't change it. And then you can select a year, for example, 20. Now we can have created a query, so we can here see the query that we will send to the, we are using the HDA API from WEkEO. So this is what we will send in, and in the next release of this plugin, it will be possible to modify the data directly in here and do the request from here if you want to. But we can then request data, and it founds for the 3 files, and the total size is 240 gigabytes. Okay. Click, and now we have listed the files down here. So we can either select all of the files, deselect, or just, if we don't want to download all, then we can just select some of those, and we can choose a folder. It will use the default folders that we have set in the settings. And then we can say download the selected files, and you can see status. It's preparing the files in the backend. And when that's ready, it will start downloading. And it's started. And you can see in the bottom, in the prominent bottom, in the Copernicus Connect, that it says download those files here. And sometimes it can take very long to download files, but you can still work in, because it's running in another thread, so you can still work in QGIS, for example. Turn off and etc. And okay, yeah, I don't know why it takes so long right now for downloading, because it's very small files, but yeah, sometimes it can take. But when it's finished, then it will have the files over in here. So yeah, I don't know if it has lost, let's see, connection. But yeah, anyway, this is what you can do in Copernicus Connect. You can download request files, select the data, search for the data sets you want to read about those. And then you can also see if they have WML, WMTS files, and you can open those directly in QGIS. I don't know if it's it's still waiting. So I'll just skip it from here, and so we can go to the QA and hopefully it will finish. So I'll stop sharing my screen.
Thanks a lot, Michel, for the presentation. So yeah, it was really interesting. We have a few questions, so from Matthew and yourself. So we will start with the first one being, well, for Matthew. So hello, why the 60-meter spatial resolution if we can get data from Sentinel-1 in 10 meters?
Yes, thank you for the question. And the reason is very simple, is that we wanted to remove some noise, or I mean to reduce the noise, I would say. That's why we went for a 60-meter resolution WEkEO product.
Okay, thanks a lot for the explanation. So the next question is more for Michael. Do we need a login name and password to QGIS plugin? What will that be then? It went too fast. So I think you mentioned we need to be a registered WEkEO, a WEkEO registered user to the Copernicus Connect.
That's right. Before you download, you could go to the WEkEO webpage and register you there. So you can self-decide your username and password. I guess there is some rules for the password, but it's a WEkEO user you have to put in. So start going to the WEkEO page and register there.
Okay.
And yeah.
Okay, so the accessible tools for WEkEO, if you don't have access, you need to be a registered user, basically.
Yeah.
Okay. So the next question,
I think
it was during your presentation. So if we have data for other countries, for example, Nepal in Asia.
Currently, we generate products for the EEA 38 plus UK domain only, but I guess it would be relevant to compute those products for Nepal or maybe Canada, but it's not part of the project.
Okay. So yeah, maybe at one point, but not for now, unfortunately. Okay. So this one, I guess it's an open question, so maybe both of you could answer. If you have an answer, what's the difference between WEkEO and the Google Earth engine? So GEE already allows users to access and manipulate Copernicus data. What is WEkEO adding to this? So yeah, I don't know if both of you could provide an answer, but on my side, I never used Google Earth engine, but what's nice with WEkEO is that you have all of the Copernicus data at the same place. So yeah, maybe it's already an advantage, but yeah, I don't know. We use Google Earth engine, so
no, I don't use Google Earth engine either.
Okay.
Me either, but one of the advantages for using it, if you are a QGIS user and you want to do the analytics and the scripting in QGIS and use all of the different plugins, then you have the data in one place, also like in WEkEO.
Okay, yeah, I agree. Thanks a lot. So yeah, I don't know if it's totally answered the questions, but yeah, maybe, yeah. I think, so for now, it's the last question. I think this one will be more for you, Mathieu. Are aggregated water and ice products different from available Copernicus river and lake ice extent, or just a new naming convention?
Yes, that's a very good point. Thank you, Michael. And indeed, the AWEek is the new product, and it's the continuity of the ARLIA product. So the project HRWSI is the new project, which is the continuity of the HRSI. So we added the water component in the project, but the products are kind of the same. Some algorithms have changed. For example, in the WEkEO2, it's completely new, but yes, indeed, it's the same philosophy. And if you use the product or if you have any question, you can still contact me, and I would be very happy to answer the questions.
Okay, thanks a lot. So yeah, just one general question. So about the PDF file and presentation. So yeah, you will have all of the PDF presentation available at the end of the day. So as Matthew said, if you have a question for him, you will be able to find his email on the last of his slides, if I'm not mistaken. And yeah, the replay will also be made available, so no worries about that. So yeah, thanks again to both of you. I think that was it for the question for you. Yeah, and thanks again for your presentations.
I'll just say there is in the slides that I didn't show, there is a documentation for how to install the plugin. So
yeah, exactly. Yeah, and Michael prepared a slide for you to help you install Copernicus Connect. It will also be made available. Thanks.
Yeah.
Okay, so we will go to the next presentation then, which is a presentation of the WEkEO tools. So the plugin WEkEO Earthkit and the graphic processing unit. So the presentation will be made by Annalena Erlman. So Annalena, I don't know if you can hear me, but you can join us to do the presentation. Oh yeah, can see you now. Hi.
Hi.
Welcome.
Thank you. It's nice to be here and see so many interested participants. Then I'll just go ahead with the presentation.
Yeah, you can share your screen.
Very good. Let me quickly share. Okay.
We can see the slides.
Okay, very good. So nice to be here. I will be presenting two of the WEkEO tools. One is the Earthkit WEkEO plugin, and the other one is a new service on the WEkEO workspace, the GPU Access. I will start with the WEkEO Earthkit plugin. First of all, if you haven't heard about it yet, so what is Earthkit? It's a Python toolkit developed by ECMWF. Designed to simplify and standardize the handling of Earth system data, so especially large-scale meteorological and climate data sets, but it can be used on other data as well, which then comes in handy for the WEkEO data sets. It consists of different modules, like the data module, where you can really streamline the access to the data, and the plots module, where you can visualize. We'll see some examples later. As I said, it's developed by ECMWF, so I'm really not the expert on the Earthkit itself, but we had in a previous WEkEO webinar the expert who is developing the Python package here. So I've just added a link to this previous webinar. So in case you're really interested or more interested about the Earthkit plugin itself, or the Earthkit tool itself, feel free to just check out James' presentation from the previous webinar. While the Earthkit Python package is developed by ECMWF for climate data, for meteorological data, WEkEO has developed some plugins, or one plugin, so that through Earthkit you can access the WEkEO data. So why would we do that? What's in it for you, for the users? So the key features are seamless data access through the WEkEO HDA, and Earthkit, which is really nice. It hides all the complexity of file management and different data formats from the user. So where before you had to download different files and then unzip files, maybe deal with the different data formats, you can now use the Earthkit to get the files and to stream it, for example, directly into an X-array. That is the second key feature, that it's possible to stream data directly or convert it directly to X-array. And what's also really handy is that you can use the Earthkit plotting functions to just create nice plots with very low effort and low code. Here are some examples how it then looks like, but I will skip this slide, and I propose we go to a nice demo of a notebook in a second. You can find some examples on how to use the WEkEO Earthkit plugin on the WEkEO workspace, like on our Jupyter Hub environment. I will quickly open that. Yes, you should be able to see that now. This is one of the example notebooks you'll find in our repository. So just to quickly show you where it's in the public folder, and when you go to WEkEO for data, and then you'll find here a whole folder for Earthkit. So just in case you want to try it later, this is where you'll find the example notebook. So we'll look at two different data sets in this example. One is coming from ECMWF and one is coming from the land monitoring service, CLMS. And the really interesting part, I'll just restart everything and run everything. And hope that it works. The really interesting part is here. So this is how you can access the WEkEO data. So you have to use the from source function and you choose WEkEO. And what is coming next is just the API request you get from the WEkEO, data viewer, for example. So if you would use the WEkEO harmonized data access, this is exactly the request you'd need as well. So it works for that. You see, it's already there. If you execute it the first time, it might take a little bit longer because the data is downloaded in the background, but I've already done this. So for me, it's in my cache. The same with the other data set, and we can just explore what we've downloaded. So we've downloaded the T2M. So this is the land. This is the temperature above at 2 meters for different dates, and the same for the other data set from the land monitoring service. And now it becomes really, really handy because with the 2xArray function, we can just convert the data we've just accessed to xArray. And you see, like we don't have to worry about any files or importing, unzipping, dealing with data formats. So that is the main advantage of Earthkit. And then once we have it in xArray, we just see something which might be familiar to many of you. When you've been working with xArray, you just have the data as an array, an n-dimensional array. And next, we will discover a bit the Earthkit plots function. So here we just we use the earthkit.plots.figure, which is all like pre-prepared for you. The only thing you need to add is like the area of interest, your units, and where you want to have the legend and the title. And just like that, you already get a really, really nice plot of the different data sets. So we are showing both different data sets for the same geographical region of Europe in one plot. What we can also do is, for example, just with changing the domains from Germany to Germany and to Spain, we can show the data in the different regions. I mean, here you can pretty nicely see Spain. Germany is not so well visible because the data is continuous, so it doesn't stop at the borders. But you can see a bit the shape of Germany here, with the Alps in the south and the North Sea and the Baltic Sea here in the north. And you can also just plot many plots next to each other, which can come very, very handy. So that is already the Earthkit plugin. Feel free to try it out. Maybe also like when you do your next ice monitoring project. I'll jump back to the slides. A bit of like information on which kind of data is supported. So for the access to the data, almost all data sets in WEkEO are supported. And then depending on how the data is structured, if it's like really, really complex data, such as some kind of very specific satellite data, then it stops there. So not all the data sets can be then directly converted to X-array or used for plotting. So you see like 80% can be converted to X-array and a bit more than 50% can be plotted directly with the Earthkit plotting functions. So just so that you know if something doesn't work directly, it can be due to the complex data structure of the data you're trying to plot, which makes it incompatible with Earthkit. And here a bit more details on like from which provider the data sets are supported. But yeah, you can take a look at that afterwards if you're interested. Now the second service I want to introduce to you today is the GPU service. So since I think it was May or June this year, we are offering graphical processing units on the WEkEO workspace, which is a very new feature, and I'm really excited about that. A bit of context. So as a user of WEkEO, so if you have an account and if you want to use the GPUs, you can. It's free for everyone. You can use them on the WEkEO workspace. It has here it says 8 GB of GPU memory, but I wanted to change that. It's more like 6-7 GB of GPU memory on the machine learning GPU server. And up to 5 users can use the GPU at the same time. So this is the limitation. If 6 people want to use the GPUs at the same time, the 6th person, they won't be able to use it as only 5 people are supported in parallel. But that is not a problem. You just wait for a little bit until the resources free up again, and then you'll be able to use them as well. So what is the intended use for the GPUs on the WEkEO workspace? So we wanted to provide those services for you to train small machine learning models, to speed up the training of small models, to prototype model training, and do inference on lightweight models. So it's not done with the expectation that you can like do all the machine learning tasks you'd like massive models, foundation models, that you can run all of that on the WEkEO workspace, but it's more of a starting point. So for you to just get familiarized with GPUs, how to set up your environments, to use GPUs and so on. So that if you want to scale up your machine learning project, you're already settled and you know what things to be aware of while using GPUs. Now a bit of tutorial on how to find the GPUs in case you want to try them. So from the landing page of the WEkEO website, you want to go to My WEkEO. So the GPU service is only available for logged in users. And then from your personal dashboard, you want to go to the WEkEO workspace here. So let me see if I can find a laser pointer. Here, the WEkEO workspace. If you click on open, you will be redirected to this options, and you want to then open the machine learning in brackets GPU server. If it is the case that already 5 people are using the GPU and you are the 6th person, I don't know if many of you are currently trying to access it, but you will probably see then this warning. Okay, so all GPU resources are already in use. The selection of machine learning GPU server will fail. Please try again later. and that's the strategy to go there. Please try again later. If you really see, okay, within 1 day or so, no free space opens up, then also feel free to write the user support or to write us a message and ask like what's up. And the GPU server on WEkEO, it looks like this. So it looks just like the it looks just like the usual WEkEO workspace, what you're maybe also already familiar with. So you see all of your data, all of your environments you might have predefined already. So you can just start working on that. And it's very important for you to know that you'll have access to all the data, because that means you could, for example, use the Earth observation server. So here, the Earth observation tools server to pre-prepare the training data and then only go to the machine learning server once you really need the GPU. There is also a bit of training material available for the GPU. You will find this here under this link. It's called Introduction to the WEkEO Workspace GPUs. And there is a collection of important tools you might want to use while monitoring the GPU usage and so on, and some really, really small examples. There is also one case study on the WEkEO Workspace GPU, how to use a vision language model for the description of satellite imagery you can try out. Now, with that being said about the GPUs, I want to introduce the Copernicus Innovation Lab to you as well. As I mentioned, the GPU server on the WEkEO workspace is more like for prototyping, just getting familiar with GPUs and the tools. And once you want to really scale up your machine learning project, you will notice, okay, the 7 GB of GPU memory on the WEkEO workspace are not enough anymore. And for this, we have the Copernicus Innovation Lab. So the Copernicus Innovation Lab is for projects of Copernicus users from the Copernicus member states. So if you are, for example, at a university in a Copernicus member state, or if you are a startup or a company within a Copernicus member state, and you are using Copernicus data and you need additional computing resources, then the Copernicus Innovation Lab could be for you. So when you apply, you will be asked to submit like a small proposal of what you would like to do and what computational resources you need for that. So for example, if you need more GPU power, if you need more CPUs, more RAM, and so on. So that is, then through the application process, we will evaluate internally if we can support your needs, if we can support your project. And then after a short amount of time, you'll hopefully receive a positive feedback from us. So in case you are looking for computational resources, if you're looking for more GPU power or more CPU power, feel free to just apply for the Copernicus Innovation Lab. And that's already it from my side. Thank you very much. I hope that was interesting. And yeah, I'm here now for you to ask your questions. Thank you.
Thanks a lot, Annalena, for your presentation. As usual, it's really interesting to learn about the WEkEO tools. And yes, so obviously we have a few questions for you. The first one being, so for the WEkEO Earthkit plugin notebook, can we alter the data we want to use? For example, LST CCA data, load that and use it in the notebook.
Yes, so you can use any kind of data through the WEkEO Earthkit plugin, you can only use the data which is available through WEkEO. So if the LST CCI data, if that is available through WEkEO, if it has a WEkEO dataset ID, you can for sure use that using the WEkEO Earthkit plugin.
Okay, thanks a lot. So we have another question about the Earthkit notebooks. So actually, we have two questions, so I will do them. The notebooks for the tutorials of Earthkit are on read-only. Do we need to download the notebooks to use them? And another question asking, so the last one, can I run a Jupyter notebook on my local machine with this data? So yeah, maybe we can do the first one actually.
Yeah.
Because...
So about the read-only, yes, that you noticed that correctly, that if you access the notebooks from the public folder, they are read-only within the public folder. So what you can do, I think the most straightforward way is to just copy the notebook from the public folder to your home directory. So maybe if I can quickly share again, then I can...
Go ahead. It will be easier.
Then I can quickly guide you through that. So here, for example, you also see that I have this notebook here in my home directory. So it's not in the public folder, but in my home directory. And once you copy it to your home directory, then you can edit it how you like. So you can then select a different data set, or you can select a different area you want to plot or so. So that's the way to do it.
Okay, thanks a lot. And yes, so the other question about the Jupyter notebook, I think it's not necessarily on the Earthkit, but on the Jupyter notebooks available on the catalog. Can I run a Jupyter notebook on my local machine with this data?
Yes, that is also possible. So what you will need on your local machine is then some kind of software that runs Jupyter notebooks. So for example, you could download through Anaconda, the Jupyter Notebook server, or you could, for example, run it in Visual Studio Code. That's how I open notebooks, or you could run it in Spider and so on. So that's what you would need for that. And also you have to take a look at the environment you need to open the notebooks. So in the WEkEO workspace, we have the environment preset for you, so you don't need to download any more Python packages, or not so many new Python packages. But when you run it on your local machine, you will have to deal with the environment yourself, how to set that up and how to install all the packages.
Okay, thanks a lot. So this one a more general question that I can partly answer. Are these datasets for only Europe, or are they for Asian country, for example, the Nepal and the Himalayan? So we had this question previously. So for the Asian region, we have data like Copernicus marine data, Copernicus land data, but concerning the Copernicus land data, I think it's mainly vegetation data like forest cover, and so I'm not sure about the ice products. I think what Mathieu told before is that for now it's mainly in Europe. Maybe at one point it would be developed for the Asian region, but yeah, for now we don't have a date. So if it's specifically on the Himalayan, I think the data available won't be of interest for you. But yeah, if you want to check marine data or anything else, you will. We have global data, so yeah, not all of the data, but yeah.
Yeah, for example, the one data set I used in the demonstration of the notebook, like the ERA 5 air temperature on 2-meter level, this is also a global product. So you can, you will have data for the whole globe.
Yeah, you will see on the second day we will have the demonstration of the WEkEO viewer. So you will be able to see a map global scale with the different products that WEkEO has available on the website. So you will also be able to see the different filters that we have. So according to the Copernicus services, the geographical region, the type of product. So if you want to have a look now, you can, but otherwise you can also wait today to have the full demonstration of the viewer. And so the last question, it was a question we had for the presentation, so I don't know if you could provide an answer to that also, Annalena. The question was why should I use WEkEO if Google Earth Engine provides capabilities to access all Copernicus data? So I didn't use Google Earth Engine. So I was thinking of, well, the Copernicus data are on WEkEO, which is a Copernicus service, but I don't know if you used yourself Google Earth Engine and could provide a better answer to that.
Yeah, I've been using Google Earth Engine a lot, especially like during my studies back then for university projects dealing with large amounts of satellite data, like the whole archive of Sentinel-2 data, for example. And it's true that Google Earth Engine, it offers many of the Copernicus data sets, especially the satellite ones like Sentinel-1, Sentinel-2, I think, meanwhile also Sentinel-3. And it's very convenient for large scale data analysis. So when you really need the access to the whole archive for long time series and so on. So it's a great tool. However, the disadvantage with Google Earth Engine is that it does not provide the original data. So it does not provide the most up-to-date data. So because, for example, I think, Mercator, as well as at EUMETSAT or as ESA, we constantly improve our data quality so that we will always have new versions of the data. And often this is not represented in Google Earth Engine because they download the data once and then they make it available for a very long time. So I think if you really want to use the best quality data, like the most recent updates of the data, then like WEkEO is the way to go because WEkEO provides the direct link to the original data provider. So you will, the data you find in WEkEO is as up to date as it is through the original providers. I think that's the main difference and that's the main advantage of WEkEO. That's all I can say to that.
Well, thanks a lot because I wasn't sure about that part, so now I'm sure. Oh, well, thanks for the answer. I think it's clearer for everyone now why to use WEkEO, at least for that part on the data quality. Yeah, so I think that was the last question concerning your presentation and WEkEO. Thanks again, Annalena, for joining us today.
Thank you.
And for the participants,
See you
don't
next
worry.
time. Ciao.
You will have the replays in the PDF, so no worries. And so now we will go do a short break, so a 5-minute break, just for you if you want to grab a coffee or chat with each other in the chat. We also advise you, so if you want to take a look at the polls, we've prepared a small word cloud for you, just to learn a bit more about you and what is the subject of your work concerning this question. So yeah, we'll see you in 5 minutes and enjoy the break. Welcome back, everyone. So we hope you had time to take a little break from the presentations, and now we will go to the use cases presentation of today, and we will start with our first use case. So welcome, Andrea.
Good morning. Good morning to everyone.
And yeah, you can start your presentation whenever you want, and thanks again for accepting the invitation.
Okay. Okay. I should have the remote control. So let's see. Okay. So good morning to everyone. I'm Andrea Spaloar from the Institute of Earth Science in Italy. I work specifically in the headquarters in Venice. And today I will bring this case of study that with the name that is climate change and impacts on the climate in Svalbard Glacier. So these works that I'm going to present, it's linked with a lot of topics because there is glaciological measurement, a bit of chemistry, monitoring, modeling, and so on. So it's a case where there is different discipline put together. But however, sorry, my mistake. So before moving into the works that I'm going to present, we need to contextualize where we are working. So in this slide, we can see the Arctic region. And in particular, I mean, this study was performed in the Svalbard archipelago. Svalbard archipelago that is located in the high North Atlantic is particularly interesting because it's at the edge of the sea ice, is influenced by different atmospheric conditions and maritime conditions as well. And in particular, if we look on the central figure where the Svalbard is indicated, we are working in the northwest portion where Ny-Ålesund, I don't know if you ever heard about this research village, is located. So in particular, if we zoom in the area where we are working, this is the, we can say, a portion of the Spitsbergen area. Ny-Ålesund is located in this, where my arrow pointing, and we are working in this ice cap that is called Holte d'Alfona. That is one of the higher ice cap in the region. So essentially, there is quite a lot of attention regarding the Svalbard archipelago, and I think most of you have already heard about the Arctic amplification. So the Arctic amplification is a phenomenon where the Arctic is warming on a faster rate compared to the global average. If you look on the chart on the left, we can see in black is the temperature, the average global temperature trend. We can say from the beginning of the 19th century to the current time. While in red, we see the temperature in Svalbard. And we see that in the last, we can say, 2 or 3 decades, the temperature in the area of the Arctic is increasing in a much faster rate compared to the global average. However, this red curve that we are looking, it's something connected to the whole Arctic. But if you are looking more a bit in detail on the Svalbard archipelago, and we're still looking on the chart on the left, we see the red curve that show the temperature anomaly compared a reference period that is the 1950 to 1980s for the whole Arctic. But if you look the blue line where we focalize only on the Svalbard archipelago, we see that while the Arctic is warming between 2 or 3 degrees in the last 2 or 3 decades, the Svalbard has increased the temperature much more, and sometimes, especially for 20 and 20, something like that, up to 6 degrees more than the global average. So the Svalbard is somehow called an hotspot for the climate change because it's changing much faster compared to the Arctic and also to the global average. So it's, as I say, it is one of the warming regions in the world, and also this rapid temperature increase affect the glacier, I mean, all the glaciers that are present in the archipelago. And we also need to consider, why is it not moving? Okay, that one of the particularity of the Svalbard Glacier, they are located at low elevation. So we are below, in the average, we are below the 1,000 meter in elevation high. So this is very exposed to the change in the low atmosphere temperature changes. So they are very exposed to the climate change. with all the consequences, so mass loss, increase of water percolation, and so on. So essentially, just to give an idea, I'm working in this context since 2012, and this is a picture of the Konnemen Glacier that is at the end of the Kongsfjorden, taken in August 2012, and you can see that, to give just a reference, this is 3 kilometers wide. And another picture taken always during the end of the summer in 2022, this is the difference that we see between in only 10 years. So the archipelago and the glacier of the archipelago is changing quite fast and quite a lot, and it's really possible to see by your eyes the changes that are occurring at the cryosphere in this area. So before entering a bit into the detail, I need to give a brief introduction of what means a natural archive and an ice core archive especially. So essentially, during the winter, we have the snow accumulation. It accumulates layer by layer, and this snow is able to trap the atmospheric composition. So if the snow survived to the summer melting, so part of the snow or the full snowpack survived to summer melting, during the next year, we have another snowpack that form another layer. And at the end, we start to have like a layering of snow, one over the other, where inside there is good information of the atmospheric composition in where this snow layer has been formed. At the end, this snow that has become compact and compact more and more, it become ice, and we drill the ice, and we collect this ice core archive where in the ice is stored the information of the past atmospheric condition. So we use this archive to study the climate impact on the signal that is preserved within this ice. And just to give an example, on the left panel is a show of a potential signal that we are able to find in an ice core archive. So if we look on the left panel, this one, we really see this oscillation of the parameter, where the more negative value of this parameter that is called the water stable isotope ratio, that is a proxy of temperature. So we see that more negative is the winter period, more positive are summer periods. So, and we see this oscillation. So this parameter here, so the water stable isotope, is able to reflect the change in the atmospheric temperature. For example, this is just a kind of, the left panel is a kind of a snapshot, but if you look on the right panel, we see that we have in red, we have the real measurement temperature, so from instrumental point of view, while in red, in gray and black, we have the reconstruct temperature by this parameter, and the two things fit pretty well. So we can extend with the ice core the temperature reconstruction in the past, also behind the instrumental record. However, the reconstruction of this past atmospheric condition or temperature need to have some requirement. We need to find the right spot. It need to be quite preserve the signal, so there shouldn't be too much melting during the summer, so the snow need to be rather preserved. And we decide to go in this ice field that is called, as I said before, the Alta del Fonna, where in the summer period, it preserves part of the snow that accumulate during the winter. So we went to this ice field. We went from 2012, 2015, 17, and 19. So we went for consecutive year. And what we measured this water stable isotope parameter. So this is in 2012, this is 2015 ice core record. So this is divided by year. So, and what we can see is that in 2012, we can see some kind of oscillation of this parameter connect with the temperature, as well in the 2015 ice core. But when we move to the core that we collect in 2017 and in 2019, this oscillation that we were able to see in 2012 and in the core collected in 2015 are completely disappear. So this means that something has happened. The site is not more usable for reconstruct or to be used to reconstruct the past climate condition, but this somehow it start to degrading. So from a signal that we can use in 10 years or less than 10 years is moved from a condition where we can use this site to reconstruct the ice, the past atmospheric condition, to a potential condition where we cannot use anymore. So to study this, how much the climate change is or is contributing to this degradation, we combine this our measurement with additional field measurement. In this case, the mass balance, so how much the glacier on our drilling site is gaining mass or losing mass, can help a lot on defining this degradation of the signal. For example, if we look on the panel C, D, and A, we have in the panel C, we have the annual mass balance. So how much the site gain mass through the year. And we see that we have an increasing of the accumulation of this of the mass at the site, where also during the summer we could have positive mass balance. So also during the summer we have a kind of increasing of snow mass. But however, this is not a condition to help us, because when we speak about increasing mass, we have much more snow that could be present in the, at the site, but at the same time we could have much more melting. So much more melting, so means having much more water that can percolate into the snow and later in the firn and ice, and really wash out the climate signal preserving the snow. To support these ideas, we can use modeling. This is a model simulation of the water percolation into the glacier. So the black line is the snow surface. We can say simulate from 1992 to 2023. And we see that where the red line is the isothermal in terms of depth, so how much the 0 degree will go into the snow. And we can see that at some point moving closer and closer to the recent period, the isothermal, so the 0 degree temperature going deeper, and also with associated increase of water percolation, that is essentially the blue color, into the deep of the glacier. So this modeling help to support the observation that we had. Finally, we also have an observation by using the R5 o comunque or the atmospheric reanalysis. We want also to check if to this increase on melting there is a change in precipitation regime. And in this case, on the right panel, we can see if there is a change in the seasonality of precipitation. But from the chart, it seems that the precipitation is rather constant through the last 30 years. So support the idea that the increase in temperature are causing an increased melting, increased percolation, and so kind of a washout of the signal within our archive. Finally, however, one thing that we are still a bit optimistic, although we are not able to see anymore the seasonal variability of this parameter that permit us to check to reconstruct the past atmospheric temperature. When we compile all the 4 records together, so we really overlap the different records together, and we compare with the annual temperature, although we are not able to see anymore the seasonal response to this parameter, to the atmospheric, to the temperature seasonal changes, and we compare that show by the black dots with the annual temperature, we still see that the record that we have, although very smooth, still respond to the increasing trend that we observe in the Svalbard archipelago. So although the signal is going to be degraded and is really deteriorating quite fast, somehow the general trend of the atmosphere is still present there. We are still able to use the site for a general reconstruction of the past temperature variability. However, in support to our field observation, we also use the satellite remote sensing for the cryosphere. And this is very important for for the work that I'm doing, because it's give an idea about which is the snow line altitude, so or how much ice has been exposed during the summer. So just to give an idea, on the left panel, we have a satellite picture from 2017, where the light blue color is the snow cover, while the blue is the bare ice. While in the August 2023, we have a much less, we can say, snow cover, indicated by the light blue, and much more bare ice exposed. So the satellite suggests that in compared 2017 and 2023, there is much less snow preserved after the summer compared to the year 2017. So this gives an important information when we are going to interpret the rest that we have from the Ice Core Climate Archive. As well, we have also the close range remote sensing, or essentially the camera. In this case, giving important when the sat is cloud cover, for example, and give an idea about how the snow change after a specific event. And also this is very important because we are able to identify when a specific event like heat waves approach the archipelago. For example, if you look this one to these differences, we have a picture of the 17th of May 2022 and another picture 23rd of May 2022. So the two pictures different of 6 days. And we see that here the snowpack is kind of uniform and pretty well distributed. But if we put quite a lot of attention, especially in this area, here we start to see some feature, and this is like a water channel that is formed after a rain event that occurred between the 17th of May and the 23rd. So this type of measurement help us to approach and go more into the detail in the evaluation of the data that we collect from the field. Finally, we also have this type of measurement that is the automatic nivometer station. This gives a continuous monitoring, automatic, of a lot of parameters of the snowpack. So we know it's at the coastal site, not on the drilling site, but at least he supports our observation, giving an idea of how the snowpack evolve and form during each season. So I would like to conclude. So the Svalbard has an increased glacier mass loss. This study is the first to assess how rising temperature in the archipelago affect climate signal preservation in the ice archive in the Svalbard archipelago. We suggest that the higher temperature boosted submelt and meltwater percolation, so washout of the climate signal present in the ice core climb. And we just remember that this degradation of the signal is happening in 7 years. So I think it's very intense, the change in Svalbard. And another point that I want to raise is that to do this type of study is essentially a multidisciplinary approach, because without all different pieces of the puzzle, it's very difficult to arrive at a robust conclusion to define how the impact of the climate change affect the ice core climate signal in this archipelago. With that, thanks for your attention, and I think I was a bit in delay.
Hi, Andrea. Thanks a lot for your presentation. And yeah, no worry about the delay. You told us about it, so it's okay. So yeah, it was really interesting. We have a few questions for you, so we will go to that part now. So the first one being a more general question about your study in general. Have you looked into the role of marine heat waves in the Barents and Nordic seas?
Okay. Do you need to reply or you need to read all before?
Sorry?
Do you need to reply to each by one?
Yeah, one by one.
Okay.
Yeah.
So to reply to this question, I mean, we thought about the marine heat waves. The things that this paper, this work, was more connected with an atmospheric component more than a marine component. So, and we thought that is interesting to look at the marine heat waves. However, it makes all the story very heavy to digest also for a potential referee, and there is too much things to put together. For sure, the marine heat waves has a role in controlling the climate and the events in the Svalbard archipelago, but we were more focusing instead to the marine heat wave that are a bit slower, we can say, to the atmospheric heat wave. So this kind of rain or snow event or this like specific condition that occur quite often. It occurs between 1 to 5 times every year in the Svalbard archipelago that bring this mild air from the southern latitudes. So we are more focusing on the atmospheric counterpart than the marine part. But I think it's something to be explored, and it's a good question.
Okay, thanks a lot. Yeah, it makes sense concerning the size of the work also. Another question, I think it was for the beginning of your presentation. Do you use a software to measure ice sheet lake cover or glacier density? Is it available online for users to use and download?
Okay, the question that do you use software to measure ice sheet lake cover?
I think
no.
Yeah.
It's no, because I'm not a modeler, so I'm not using this type of software. I want to be honest. The glacier density, it can be, I can say, modeled, but we use the measurement because the density is not an exponential line, as we can say, a theoretical exponential line. This type of glacier has a lot of firn ice layers, so there is a lot of discontinuity in the density increase, and it's not easy to reproduce. So we prefer to measure the density because it's in 20 centimeter, you can have a layer of 0.5 or 500 kilometer per meter cube density and like 0.900 kilogram. So it's very variable. Obviously, it increases with the depth, but it's not so linear as a classical density increase.
Okay, thanks a lot. Okay, another question, more specific one. Have you considered using microwave LST data to look at the emissivity differences over the region AMSR and SSMI? Emissivity could help with classification.
We thought, because I have some people working with this type of measurement, but as said, it's very complex sometimes to connect the field data, atmospheric reanalysis, ice modeling, and also with this type of measurement. So it's something that is interesting. Everything that can be put together and give some more information is very helpful. But we need to be also realistic when we produce a product like the paper that they present. So we need to be at some point focusing on some part. We are doing some extension using these techniques, but it takes a bit more time.
Okay, thanks a lot. Okay, and so the last question for now, have you assessed whether this increased ice loss is attributed to increased melting or to increased ice discharge due to calving?
Okay, this is both, I want to say, because for example, I show a picture showing the difference between a glacier in 2012 and 2022. This is a floating glacier, so there is a lot of calving over there. And part of this glacier mass loss is due by calving. But as well, so I would say both, because there is most of the glacier in Svalbard are temperate. So if you have melting, the water percolate almost through the entire glacier and will be discharged into the seawater. So I will say that is both. I'm not sure if which is winning. I mean, if it's more ice loss or the increase of calving, for example. So there is another thing that the increase of melting increase the speed of some glacier. So there is some glaciers start surging because it's like you have a lubrication effect on the bottom. I think that is not super easy to assess which is if increase means melting or increased ice discharge. So for example, for the small glacier, like the ground glacier, there are a lot of small glaciers in Svalbard, the melting is winning. So there is no calving in this glacier, and they are losing like at the bottom is losing up to 3 meter water equivalent per year. In the upper part, 1 meter. So this is fully melting. Obviously, the glacier that are discharging or arriving into the fjord, into the sea, this is different because there is the calving that is quite important, but as well, I mean, also the melting as an effect. It's difficult to say. I mean, there are some studies in specific glacier where it seems the melting is a bit more efficient, but obviously this is just one case over 1,000 glaciers in Svalbard.
Okay. Okay, thanks a lot for the explanation. I think it's clearer for the participant now. So that was the last question for you, Andrea. Thanks again for joining us today. And yes, so for the participants, you will have Andrea presentation. It will be made available today, so you will be able to see the different references presented during during the event. So yeah, you will be able to learn more about the work Andrea does at the Institute of Polar Science. Yeah, thanks again, Andrea, for joining us, and have a nice day.
Thanks. Bye.
Bye. So now we will go to the second use case of today. So yeah, I welcome Etienne from the French National Research Center, and yeah, Etienne will present to you his work on the Pléiades Glacier Observatory. And welcome, Etienne, and you can start your presentation whenever you're ready.
Okay, can you hear me, Gail?
Yeah, we can hear you.
Excellent. And let's see if I have the control of the slide. Yes, perfect. Yeah, thanks a lot for the invitation and the chance to present a monitoring program using Pléiades satellite images. I'm a CNRS researcher. I work in Toulouse, southwest of France, in Lagos, which is one of the laboratory of Observatoire Midi-Pyrénées. And I want to illustrate how we provide to the community a resolution digital elevation model and ortho images from very high resolution images from Pléiades. The context was already nicely introduced by Andrea in his talk. Is that glaciers are really under pressure of global warming. This is a complex figure from a paper published back in 2021 that show a comprehensive view of glacier mass loss on Earth. So the size of each square is proportional to the mass loss of each region on Earth. So you can see that Svalbard in the far north are indeed losing mass, but everywhere on Earth, glaciers are losing ice. So that at a global scale, for this period of 20 years, from 2000 to 2020, they lost 260 gigatons per year. It probably doesn't tell you a lot, but this is equivalent to 3 Olympic swimming pools lost every second. And this is lost to the ocean. So glaciers are contributing to sea level rise about 3/4 of a millimeter per year. This is about 20% of sea level rise. Important to remind here, we look at glacier, what some people call sometimes mountain glacier, but this excludes the 2 polar ice sheets of Greenland and Antarctica, which are also contributing a large fraction of sea level rise. But here, the presentation and our observatory focus on glacier. This mass loss of glacier is also accelerating. For example, in year 2023, in an update assessment made by a community effort called the Glamby team, we showed that for year 2023, the mass loss of glacier reached as much as 550 gigatons per year, so double the amount during the previous 20 years. And in this assessment, we showed that glaciers in the Alps in the Pyrenees have lost 40% of their volume in less than a quarter of a century. So just to illustrate that glacier mass loss is going very fast. So glaciologists have developed a different method to weight the glacier to measure their mass balance. Of course, the first one coming to your mind is based on in situ measurement. This has been used for decades to measure the change of mass of about now 100 glaciers on Earth. But of course, these 100 glaciers, it's difficult to know to what extent they are representative of the 200,000 glaciers or more that you find on the Earth's surface. And most of the measurements are made on small glaciers, which are easy to access. So this raises the question of whether those measurements in the field are representative. So the community has developed over the last 20 years several techniques to measure glaciers from space, measure their mass balance. I don't have time here to go into detail of each of these techniques, but I refer you to a review paper we wrote back in 2023 in Report on Progress in Physics that detail each of these methods, its strengths and weaknesses. Here I will focus only on the last method, which is sometimes referred to as the geodetic method or the DM differencing method. This is a method that we've been using in Toulouse to look at glacier change. It gives high spatial resolution, as I will explain, and allow measuring glacier over a long time period at the global scale. To illustrate the principle of this method, I show this animation showing the change of the mer de glace. This is a glacier tongue in the French Alps between 2003, 2012, and 2022. This is derived from images and digital elevation model from Pleiades in 2012 and 2022, and SPOT5 in 23. I think you can easily see that those topographic data and the associated images can allow measuring the change both of the retreat of the glacier front with this yellow arrow here, and also the thinning of the tongue of the glacier, which is really obvious during this 20-year time period. So this is the technique that we are going to use, produce digital elevation model, topography of the glacier, and make the difference between them to look at glacier elevation change with time. We can integrate the elevation change over the entire surface of the glacier and convert this to the mass balance of the glacier with an assumption of the density of the material which was lost or gained, whether it is ice or fern. So the question you could ask is, why did we need a special project? Why did we need the Pleiades Glacier Observatory and a special acquisition program? This is because we rely on data, high-resolution stereoscopic data, such as from Pleiades. So they have a high potential for glacier monitoring, but they come from commercial satellites. So in the case of Pleiades, they are operated by Airbus Defence and Space. So there is no systematic acquisition program. The satellite will acquire images only when a user is asking for the satellite to do so and when the user is actually paying for it. So the idea of the program, supported by the French Space Agency CNES and this data initiative called Dynamis in France, to facilitate access to satellite high-resolution images. So the idea was to make sure some images of glacier were acquired at the end of the summer, so the right time of the year. This is the time of the year when you have less snow on the glacier and where you can really distinguish the glacier and measure them as best as possible. And of course, the goal of the project was not only to acquire the images, but also to deliver the images and the digital elevation model to the community. A few words about the Pleiades satellites. So they were developed by CNES, operated by Airbus Defence and Space, as I said before. There are two satellites launched in 2011 and 2012, and they will fly until 2028. So those are very high resolution data with a panchromatic channel of 0.5 meter resolution that I will focus on today, and the multispectral images have a coarser resolution. And one characteristic of Pleiades is that it has a very high agility along its orbit. And as you can see here, you can see the same scene from two different points of view by rolling along the orbit, which permit to generate a stereoscopic pair. So two images of the same part of the ground, but from different point of view. How do those images look like? This is some of the first images we got over a glacier back in 2012. And what you can see here on your screen is you can see some black dots, which are aligned along a straight white line. This is end of the morning in August 2012 over the Mont Blanc area. And because we have a stereoscopic pair, so two images acquire 30 seconds apart, we can make an animation. And as you can see, some dots are moving, other not, towards the summit of Mont Blanc. And as you already guessed, these are mountaineers who are heading towards the summit of Mont Blanc. It shows the level of resolution that we get from those images. Maybe very interesting also for you is to note on the upper right corner, if I animate the images, you can see that the crevasses don't look the same in both images. This is the result, the stereoscopic effect, the fact that the images are taken from two different points of view. And this is the property that we're going to use to generate accurate digital elevation model of the glacier surface. So this is the kind of data that we collect in the Pleiad Glacier Observatory program. This started back in 2016. And during the first 5 years, what we did is a first coverage of 140 sites that we selected all around the Earth. They are covered with a bit more than 280 stereopair. And in total, we cover 20,000 square kilometers of glacier, once again, outside the ice sheet. This is quite a lot. It's still small compared to the total coverage of glacier on Earth, but this is what we could get given the funding available in this program. And then after 5 years, we enter into revisits. It means that every 5 years, we map again a site that was seen 5 years before to look at glacier change over this period. So the product we deliver, with the example of an ice cap in Arctic Canada, we generate digital surface model or elevation model at 2 resolution, 2 meters and 20 meters. They are produced using a photogrammetric software, open source called Amester pipeline with 2 different algorithms. Very important for us is that all our product, all digital elevation model are referenced to the Copernicus 30-meter global DM freely available from the Copernicus. And this is important. It means that it creates some homogeneity in our database. It means that the DM are readily usable because they can be compared to other data sources, other topographic data. And we also generate ortho images at 0.5 meter resolution or 2 meter for the multispectral images. As I said before, 5 years later, we come back to the sites, acquire some images, cloud permitting, of course, and then we generate a new digital elevation model. We make correlation, alignment of the DM, and can make the difference between them to generate an added value product, which is a map of elevation change. Here for this ice cap in Canada. In yellow, you have the stable terrain around the ice cap, and you can see that the noise level is very small. And in red, you can clearly see the thinning of the ice cap. And this is also a product we also provide to the community. We did quite some work in estimating the uncertainty of those DM. And we were lucky to have some airborne LiDAR, which is really the best topographic data that you can really get. And we were lucky to have them almost the same day as the acquisition from Pleiades, so the Pleiad Glacier Observatory product. So in Canada, they were acquired just on the same day, and in Norway, just 1 day apart. It allows, it's very important to have a reference data, validation data on almost the same day or within a few hours, because glaciers are changing constantly due to accumulation or melt. So you really want your reference data to be acquired within a very short time span. So we can, based on those reference data, we can make the difference between the PGO, Pleiad Glacier Observatory, DM, and the reference data, and look at those maps of elevation difference. It shows an uncertainty of a few tenths of centimeters from our topography derived from spaceborne data. And very interestingly, we show that the off-glacier terrain is a conservative proxy for the uncertainty. It's important for us because usually you don't have LiDAR data at the same time of your satellite data. So it means that we can use the stable terrain around the glacier as a proxy for uncertainty and propagate this to the glacier terrain. If you want to know more about this acquisition program and the data we provide to the community, I invite you to visit our website, the Pleiad Glacier Observatory website. We describe the product. We describe also in detail how to access the data. That access is maybe not as easy as we would like, but still they are the DM are all open source, but you need to register to sign in to get access to the data. And we also advertise a publication coming from the community and make a gallery of a different product. When we have new nice images or new nice results, we post them on the website. And so this is the main site to visit, and especially a tutorial to get access to the data. And then you will be linked to a database which is based in Strasbourg, where you will have access to the digital elevation model, the elevation difference map. If you want a very high resolution images associated to the DM, you will need to sign a license because they are considered as sensible product by your defense service. So you need to register to sign a license before accessing to this data. Further detail are available in a paper we published last year presenting the whole program with a bit more, of course, at what I could present today. In particular, we look at whether those 140 sites spread all around the Earth, to what extent they are representative of the 200,000 glaciers on Earth. And to conclude, I hope I convince you that DM from high resolution stereoscopic images are a key tool to monitor glacier change. As I said before, Pleiad is going to fly until 2028. So we have to think right now about the continuity of our monitoring program, and this should be ensured by a new constellation launched by the French Space Agency called CO3D. You can see a view on the left panel. This is 2 pairs of satellites which are dedicated to the measurement of the topography on Earth. And the first aim is really to build a global topography of the Earth at very high resolution. But for some of our sites, from glacier sites, we will have some revisit, more frequent revisit to go on monitoring the evolution of glacier. So this is on the short term, but on the long term, we are also advocating for a space mission that we name 4D Earth to really monitor every month or every 2 months the evolving topography of the Earth. This is not only a mission dedicated to glacier, it's also looking at the ice sheet, of course, and also any change that can occur at the Earth's surface. It could be a change in the height of the canopy, it could be change of the Earth's surface due to landslide, due to volcanoes, due to earthquake. And yes, do not hesitate to contact us if you have any question. And I want to acknowledge Anne Guyet is also working with me in Toulouse on the Pleiad Glacier Observatory program. Thank you for your attention.
Thanks a lot, Etienne, for the presentation. It was really interesting to see the presentation of this project. And yeah, we have a few questions for you. So we'll go to the question. So the first one, so you answered already during your conclusion, so saying the project end in 2028. So you said there will be a follow-up to this project. Do you know for how long the project will last, or do you just know it will start in 2028?
Yes, so there's this new constellation called CO3D that should basically have similar characteristic as Pleiades satellites. So we are hoping, it's not secure yet, that we'll be able to maintain the measurement on those 140 sites on Earth to ensure continuity. For some sites, we hope to have a more frequent revisit than 5 years. Of course, it would be super interesting to look at seasonal change of glacier. So we always want to do more, but this is not going to be possible for all those sites. But for dedicated sites, we hope to have so a follow-up program at even higher resolution. And CO3D is, I think, planned for 5 or 7 years. This is the initial lifetime of the satellite, but generally, if they work well, it can be extended further in time, hopefully.
Okay, thanks a lot. So a more general question, how can you be part of a similar project? Or can we, as users, I guess?
If how people can be involved, of course, people can be involved by downloading the data, working with them. That's the first step. The set of target of the Pleiad Glacier Observatory is already set. We cannot add a new targets now because we want to go on monitoring those sites and ensure the continuity of those sites. So we cannot add more for funding reasons. But people can also order their own images. At least colleagues from European Union can access Pléiades at relatively reduced cost. So they can contact me if they want to acquire images of the site of interest, and maybe I can help.
Okay, thanks a lot.
Yes, good question. Other glacier, yes. So first of all, people can check the catalog. It's available. Everybody can check the catalog of Pléiades. It's named GeoStore. They can check if their site was acquired by Pléiades. The good news is that within a few months, years, the entire archive of Pléiades is going to be accessible. It's named a program by the CNES, which is named the Pléiades World Heritage. It's not the case right now, but if there is an emergency to get access to those data, people can, again, especially from European Union, can access the images in the catalog. There is a small cost associated to that, but they can access to that. And for colleagues outside Europe, basically they need to have a collaborator in Europe that can do they can access the data. And if they collaborate, it's possible.
Okay, thanks.
Alors, yes, Pléiades. It's a common problem from optical images that it doesn't work well in area of low contrast. This was the case in all images. There were 8-bit images. They were coded. They were problematic to process when there was little contrast. But to be short, with the new generation of satellite like Pléiades, you still have a lot of contrast, a lot of feature in the images in the upper accumulation area. So we have almost complete DM, even over the very flat ice sheet, even the very flat accumulation area. The DM are generally almost complete. And again, I refer to the review paper we wrote in 2023 when we detail that. So yes, and the errors are small, yes, in this upper part.
Okay, thanks. And so, yeah, the last question. So it's a more general question, so I think I can answer that. You showed that we can retrieve the data through your own website, Get Data, but will it also be made available through WEkEO? So on WEkEO, you will find Copernicus data mainly. Sometimes a few external data are also available on the website. So I don't know if this exact data will be made available, but in the meantime, you can use Etienne website if you want to check the data. So yeah, you will be able to, I guess it's explained on the website how to download the data. So yeah, if you want to have a look, you will need to go through Etienne website. And yes, so that was it for the question concerning your presentation. Thanks again for joining us today.
Thanks a lot.
Thanks. And yes, so now we will go to the last use case of today, which is a presentation by Michel Tsamados from the University College of London. Welcome, Michel.
Hello, everyone.
And whenever you're ready, you can start your presentation about Sentinel-3.
You hear me well?
Yeah, we can hear you well.
Okay, thanks for having me. So yeah, I will follow on these lovely talks and talk to you about Sentinel-3 for sea ice monitoring. So we're moving from glaciers and land ice and looking at sea ice. I'm Michel Tsamados. I'm associate professor at UCL in the Department of Earth Sciences. So really, this talk is an homage and credit to an amazing mission, or two amazing missions called Sentinel-3 from the Copernicus program. So let me see if I can actually go to the next slide. Okay, so the other speakers did a great job in introducing the concept of Arctic amplification, but I'm going to take you again and zoom in the Arctic Ocean. The Arctic Ocean is this frozen ocean around the North Pole, really. And so here I did a little schematic showing to you the maximum extent of the sea ice at the end of the winter, and it's about 14 million square kilometers. And if you look at the end of the summer, you have a shrink, the sea ice shrinks and melts, and we have about 4 million square kilometers. So this is happening every year. There's a kind of breathing pattern. The fact that the sea ice is declining, you might have heard about it, and is primarily driven by warming of the Arctic temperatures. They are warming much faster than the rest of the planet, up to 4 times faster. This is what is referred to as Arctic amplification. Actually, if you compare the last 20 years from 1990 to 2010, actually this 20-year difference in period, you have regions in the Arctic that have warmed by up to 5 degrees on a yearly average. So this is unheard of, and it's the only place on Earth really that is so intensely warming. And so this results in retreat of sea ice. Here you see regions that have lost up to half of the coverage, and places like north of Russia, Murmansk and so on might have no more sea ice now in the winter, which is totally changing the landscape, the local landscape. So, but the extent is a kind of simplistic view of the Arctic, right? It's a white map, a 2D map of where there is ice or no ice. But actually what also matters is how thick this ice is. So our team and our university for many years now have been pioneers, and also Lagos, actually the group of Etienne, in the past have been pioneers in monitoring the thickness of the ice from satellites. And so today I will cover also that from, it's a tool called altimetry. So we use altimetry to measure the thickness of the ice. So this is a little schematic showing to you where is the thick ice. So orange is the thickest ice remaining, and it's about 3-4 meters north of Greenland, north of the Canadian Arctic. The remaining ice can be very thin, just a few tens of centimeters in the Russian sector, typically. So it's important to monitor the thickness, not just the extent. That's the message I want to say. Now, if we want to predict when the sea ice will disappear, I was working on sea ice since the 2010, and when I first worked on sea ice, there was this kind of graphic of the declining sea ice extent in September. And so people were very, very worried, and they were doing some simple extrapolation of this decline, rapid decline. And some people had predicted that the ice will disappear by now. So this red line is 1 million square kilometer. And if it crosses that line, we tend to say the sea ice has disappeared. And I was worried as well. But actually, in the last 10 years, something has happened, which is called, chaotic, the chaotic nature of the climate. There are many timescales, and one of them is decadal variability. And so the sea ice has actually slowed down in terms of extent, in declining in extent in the last 15 years. This is something that was documented and published earlier this year. But actually, this is not a happy story, really. The sea ice is melting rapidly still. And so if you look at the volume, the sea ice continues to rapidly decline. So don't take that as a happy story. And also, this is predicted to continue to decline in the future. But yeah, let me tell you what I will talk about. Sentinel-3. And again, Sentinel-3 is an amazing pair of satellites, A and B. They've been launched almost 10 years ago, the first one, and 7 years ago, the second one. And so there are different modes of operation for the altimetry part of this satellite. SAR mode is really the legacy of CryoSat-2. It's a high-resolution altimetry mode that allows you to measure the elevation within a narrow localization. So I will tell you about these two satellites and how we came about to use them and what kind of results we found with them. The other amazing thing with Sentinel-3, again, a Copernicus mission really, is that there is many instruments on board. So the synergy of data that you can collect with this pair of satellites is amazing. So here I will only have time to cover optical and altimetry, but I have a few slides on passive microwave and thermal, which are the two other instruments you have on board Sentinel-3. But if you have questions, I'm happy to take on the other topics as well. So I'll start with optical, and there is an instrument called OLCI. And so with this instrument, I'll play you a little video. If you follow the satellite, you can see really the surface of if there are no clouds, you can see the surface of the sea ice in that case. Here we're crossing the Alaska from the Bering Strait to the Pacific Ocean, and we see really where there is ice, when there is no ice, when there is fragmentation of ice, and we can estimate the concentration of sea ice that way. But the resolution is 300 meters, right? So we have developed new products based on that, but this remains a limit. 300 meters is high resolution, but it's also low, can also be seen as a low resolution if you want to do, for example, navigation or very high resolution needs are required. So what we proposed a few years back, 2 years ago, was to try this technique in the area of machine learning, in the age of machine learning, to try and super resolve these Sentinel-3 images. So the bottom pixelated image here is a Sentinel-3 image at 300 meter pixel resolution, and the top is a Sentinel-2 collocated image at 10 meter resolution. So a huge factor of enhancement, a factor almost 30 by 30,000 increase in resolution. So the challenge we asked ourselves is, if we train with hundreds of thousands of images collocated between Sentinel-3 and Sentinel-2, could we use what is called generative adversarial networks to create high-resolution images, invent essentially an image that is of the Sentinel-2 type? And so we tried that, and we had some success with mountains in particular, so perhaps something Etienne and Andrea could be interested in. We were able to take a pixelated image and invent those kind of images. This worked quite well, but it wasn't working so well for sea ice. Until this year, when we moved to diffusion models, and it's a kind of latest flavor of kind of machine learning models for generative approaches, and we were able now to really turn a pixelated image, as you see on the top, to something look like the truth, which is the middle row. In the bottom, we made a prediction from the pixelated image of Sentinel-3, and so we were very happy to see this preliminary result. So this is in preparation at the moment. So you can really, perhaps you don't see the exact truth, but you see something that looks very realistic and might be very important for models, for applications of all kinds. So that's an interesting example of optical applications. Now I'll move to altimetry applications. Remember, this is to measure the thickness, the third dimension, really, elevation of the ocean or of the sea ice. And our first example is a good example, actually, because it's a synergy between optical data and altimetry. Remember that Sentinel-3 has several sensors exactly collocated. And this is amazing when you look at sea ice, because sea ice is moving very fast. Unlike, I mean, glaciers are moving faster and faster, but sea ice is moving sometimes up to 1 meter per second. So having the two instruments at the exact same time is very good for things like machine learning and training and so on. So here I give you an example of cracks. You see the black things are cracks in the ice, which is open ocean. And the two squiggly lines you see are echoes from the altimeter. So a very sharp echo will correspond to a crack or an open ocean that is very flat and reflective, while a more diffuse echo on the top is sea ice. So we're able to really classify blue dots in this line and red dots, which are sea ice and leads. And we combine that with the optical imagery to really enhance the whole coverage of our optical image in terms of classification. So this was a paper published about 2 years ago, a year ago, by Weibin Chen, my PhD student. Now, altimetry is quite complex. So to really understand these squiggly lines I'm showing you on the right here, the blue lines, these are called echoes, and they are the response of the radar bouncing off the surface of the ice and coming back to the satellite, in that case, Sentinel-3. So what we were able to do with colleagues in Norway, Jack Land in particular, is to create a direct numerical simulation of these echoes for real CS and any topography, really. And we were happy to see that our model, the bottom line, corresponds very nicely to the real echoes. So this gives us a lot of confidence that we can really understand the properties of the ice, the topography, the roughness, but also the thickness of the ice. So we're able to process a lot of data of that type to make along these tracks, measure the freeboard, the thickness of the ice. The problem is that, as you see on those plots, satellite altimetry suffers from the fact that it's a reasonably localized technique. So you have a track and you measure the elevation and the thickness just at the location of the track. So you see here, for example, the white parts are thicker ice with a freeboard of 30 centimeter wide. Blue are thinner ice. So what really people want is a map, continuous map in time and space of the whole Arctic Ocean, right? So is there a way to interpolate the data in a kind of statistically robust way to create maps such as those, but everywhere, every day? So what we propose to do is to use probabilistic machine learning, and in particular Gaussian processes, to learn the spatial and temporal correlation patterns in this data, to use them to extrapolate or interpolate the data everywhere in space and time. And so we launched a software called GPSat, and that has been very successful. And we now are able to interpolate the data everywhere in time and space. And that was published 4 years ago, actually. And so now we have this technique, we can make those maps, and you see now we have with Sentinel-3 A and B on the left, lovely map for a given day of the freeboard everywhere. If we add a third Sentinel-3, and so that was something that the European Space Agency and the European program asked us, how will we improve the map? So this is Sentinel-3 Sentinel-3C is planned for launch in the future, and so we wanted to see how much we will gain in that. So we did the kind of simulation here. And we found that the uncertainty when you add the third satellite is reduced. The map is, as you can see, it's getting bluer a little bit everywhere. So this shows to you that the synergy of satellites can also help you improve more and more the quality of your retrievals when it comes to CIS thickness. So you can find out more about this in our paper last year in Nature Communications, and on the software, the algorithm is open source, GPSat, check it out. Now, the same kind of techniques, we've expanded it, and here I must admit that the maths were done by my student Wei Bin Chen and my colleague So Takao and others. But what we showed is that you can use deep learning to kind of simulate these Gaussian processes in a way that's much more effective, and also to account of the full spherical nature of the Earth. And here we did a test on ocean elevation. So as you know, the ocean has highs and lows, and some of them are eddies, circulating features of the ocean. And so the left map shows the tracks of the altimeter. And so what we set out to do was to try and interpolate again everywhere at any given place, at any given time, if we could see the topographics, highs and lows of the ocean. This is also particularly interesting when you look at sea level rise on the longer term, but these features are also changing on a kind of daily basis. So the DRF map on the top right is showing to you the latest technique we developed, and the GP method in the middle is showing what we were able to achieve before. So deep random features really enhance the resolution, and the uncertainty you can see at the bottom is comparable, but the really capturing these eddies, mesoscopic eddies, is a kind of revolution in its own right. And we continue to validate and assess the quality of this technique, but we are very happy to see those kind of results. So just to kind of wrap up, I want to again pay homage to Sentinel-3 and its multi-sensor approach, which is, again, in the age of AI, extremely useful to learn from different sensors how they speak to each other, really. And I will just tell you that all of the results I've shown are a team effort. Don't hesitate to reach out to me for questions. I hope I have questions today. I'll just say as well that because I have 30 seconds left, just to give you a little flavor of passive microwave. Passive microwave was, for us, useful to retrieve snow on sea ice thickness. So we did a lot of work with Sentinel-3 A and B on that, but also to retrieve sea ice concentration. So you can see in this movie that Sentinel-3, just by itself, can be an amazing technique to monitor the extent, this kind of 2D map I was telling you about, where there is ice and how much its concentration is. And finally, just to give you a sense of something I work less on, that there is also a thermal camera on Sentinel-3. So you can see the temperature of the surface. And this is amazing at 1 kilometer resolution. And this is amazing to detect features like open ocean or ice. So I'm going to leave it at this and come back to my summary slide. Thank you very much.
Thanks a lot, Michel, for your presentation. It was really interesting to see a presentation about the sea ice. And yeah, so for now, we have only one question. So I will display it. Can you explain a bit more of how the sea ice thickness is measured, please, especially if there is snow cover above? So I think you showed maybe one extra slides with the full figure.
Maybe I should go back to this if you can Can you allow me to go back to this? Hang on. How do I...
Yeah, normally you should be able to share the screen.
I share my screen.
No, you can. Yeah, you can. We will go on the slide. No worries. My bad.
Yeah. So you need to remove the question, or do I go?
No worries. It will be.
Yeah. But that's an excellent question. Yeah, maybe go one before or two before this one. Yeah, I can do it. Yeah. So yeah, that's an excellent question. I realized I went quick on measuring thickness for the interest of time. Measuring thickness is actually, hang on, I need to go back one slide. For some reason, one more slide back. Yeah, here we go. So measuring thickness is a very challenging problem. It took 30 years in our team at UCL to achieve something that is at a very high resolution, but especially because you have snow on ice. So what we do in a nutshell, we have a radar. The radar is measuring the distance from the satellite to the top of the ice, assuming it penetrates the snow totally, which is usually kind of right. And then you measure the distance from the satellite to the blue, to the ocean, in these cracks, in these leads that I showed. And this little difference of elevation is what we call freeboard. And Archimedes, a Greek guy, showed us many thousands of years ago that an ice cube that is floating has about 90% of the ice below the level of the ocean. So you can kind of calculate the total thickness from what is the amount of ice that sticks out of the ocean that you can measure from space, which is amazing because you measure of the order of 10 centimeters from 700-kilometer altitude. So it's a technological achievement, really. So yeah, that's in a nutshell, how we do it. Lost you for a second. Okay, can you hear me, Gael?
Gael is
My
muted.
bad. Yeah. But no, yeah, we're just reading the question. But yeah, it's so the University of Leicester would like to know if it'd be interesting in a collaboration.
Which university? Yes is the answer, but just
Leicester?
Leicester, yeah, of course. Yeah, amazing, especially because they work on yeah, Leicester is a trick. You shouldn't say Leicester, it's Leicester.
Yeah.
But it's a SLSTR is the thermal camera, the thermal data I was talking about. So that would be very, very interesting to collaborate because this is the thing I work the least on. So yeah, very happy to collaborate. Just drop me an email and we're in the same country. So I'm based in the UK as well. And that would be great.
Okay, good news. Yeah. I think your email is available on the slides also. So okay.
Yeah.
Okay. Another question: why is the uncertainty of freeboard 8 larger in coastal areas and in narrow passages higher than in the free ocean? Is the SRAL sensor nadir looking?
Sounds like it's quite technical question, but
Yeah.
I can answer. There is, in particular, for when you monitor sea surface height, when you come close to the coast and also sea ice, the footprint of the radar is quite large. It can be 300 meter a long track and a few kilometers across track. So if you interfere, if you measure ocean and then there is land on the side, a mountain or something, or even vegetation, it can affect your signal, right? So you can have a land contamination, as we say. Another issue is that, of course, for sea level measurement, there are processes that are very specific to coastal regions. So sea level rise in the coasts, which is the most important for populations, for the million of people who live, or billion of people who live in the coast and will be subjected to sea level rise. The sea level rise is different, needs to be adjusted and understood. So these are the two main reasons why there are larger uncertainties of sea surface height. Now for freeboard, it is mostly the land contamination issue. I work, for example, with Inuit people in fast ice in channels of the high Arctic in Canada. And the channels are a few kilometers wide. And so for some of these channels, it is quite hard for altimetry to work. There are, or at least radar altimetry. There are laser altimeters like ISA2 that have a smaller footprint of the order of tens of centimeters or meters, and then you can actually use them. And there are other satellite techniques, and sometimes proxies of thickness that you can try and use. But yeah, that's my short answer. It is difficult. And as you saw in my maps, the uncertainty was larger near the coast, mostly due to coastal contamination and lack of data, because you have less data.
Yeah, thanks a lot. Yeah, it's usual to have a bit of issues around the coast with the satellite data. So we have this question, could you use diffusion models above mountains, like for the sea ice, or is it not necessary or too expensive?
Yeah, good question. I'm a sea ice expert. That's why I started with sea ice. But as you saw, I did it also for mountain ranges. You can use diffusion model in different applications, right? So here it was more for optical imagery. So we were making images of mountains and things like that. Etienne showed some amazing digital elevation models. And so we are working also on digital elevation models for sea ice from diffusion models, and it works. I'd love to work with Etienne to discuss these questions. The short answer is yes. Is it too expensive? This is a good question. In the age of AI, we should be careful with not wasting resources, computational resources. Often with models, AI can be quicker at inference or at running the model, but it can take quite a lot of time to train the model. And actually, diffusion models are a special breed. They are actually also quite expensive at running, at deploying. So I think there needs to be a good budgeting of how much this is costing in terms of CO2, water resources, and so on. And we shouldn't be wasteful when we do these things. We should also consider that. So it's a very good question. Yeah.
Thanks a lot. So that was the last question for your presentation. Yeah, it's the last. Thanks again for the presentation and your participation.
Thank you for organizing.
Yeah, so yeah, thanks again to everyone who joined us today and presented their work. For the participants, we are reaching the end of today's session, so we hope you found the session useful and informative. So before you leave, I just want to remind you that there is a section on the website next to the Q&A reserved to the poll, so we would really appreciate to have your feedback on today. And concerning the practical session, it will be the day after tomorrow. So if you haven't had time yet, I invite you to check the full tutorials and to practice. So the tutorials are available in full on the event website, along with the video demonstration. So yeah, you will find Jupyter, QGIS, and Earth sections, all of them using Copernicus data. So yeah, on day 2, it will be only a short presentation of these tutorials. And yeah, concerning the presentations and the replay, you will be notified by email once it's available, and you will be able to check everything we showed you today. So thanks again to everyone for joining, and see you in 2 days. Bye.